Make the Stick Jump is an Aboriginal game that is played and practiced all over North America, more specifically, tribal areas in northern Canada. The game originated as a way for young children to begin to learn the basics of hunting and aiming, but developed into so much more. Unexpected positive outcomes that came from playing this sport is that it brings families together, teaches individuals basic math, and develops hand-eye coordination that could be held onto for the rest of one's life. The game involves very limited materials and space. All that is needed is a predetermined amount of beanbags, sticks, and a grass or dirt playing surface around 20 meters long and 10 meters wide, but could be altered depending on the personal situation. Ultimately, the game is very simple. It could be played individually, in pairs, or in teams. The usual amount of sticks and beanbags are 5 of each. All of the sticks are stuck into the ground directly in front of the player and have a space of 5 meters between each other. The basic objective is to knock down the sticks with the beanbag from the closest stick to the furthest stick. The closest stick is worth 1 point, and each stick after that is worth 1 more point than the one before it. One team throws 5 beanbags and calculates the amount of points that they collected. Then the other team has their turn. The team with the most points wins the game. Throughout my informative presentation, I will be describing the impact of kinematics, kinetics, momentum and energy, and fields on the Aboriginal game Make the Stick Jump. I will also be explaining what happens to these topics on a planet with more gravitational strength than Earth and a planet with less gravitational field strength than Earth. I'm using the planets of Mars and Neptune to demonstrate this. The gravitational field strength for these planets are 9.8 meters per second squared for Earth, 3.7 meters per second squared for Mars, and 11.2 meters per second squared for Neptune. To begin, the concepts and ideas of kinematics are seen greatly throughout Make the Stick Jump. When throwing the beanbag in attempt to hit a stick, a parabolic trend is always seen. There are horizontal and vertical components of the trajectory of every beanbag thrown. Here are 3 kinematic trend graphs for vertical components. They are the relationships between time and displacement, time and velocity, and time and acceleration of a projectile from Make the Stick Jump. It is seen that when the beanbag is released, its displacement begins to increase at its fastest rate. At the same time, the velocity is at its maximum speed, and the acceleration is at negative 9.8 meters per second squared. At the maximum height of the projectile, the beanbag does not have vertical motion. The velocity is 0 meters per second, and the acceleration remains constant. At the end of the parabola, the slope of the displacement is at the same value as the initial displacement. The velocity becomes negative because it is a vector, and up is positive, and the acceleration does not change from negative 9.8 meters per second squared. Now I will be going over some equations based on the topic. The first question is asking to find the maximum height of the beanbag. I am given the acceleration due to gravity, the velocity, and the angle of the projectile. The first step I did was splitting up the velocity into horizontal and vertical velocities. I knew that at the maximum height, the vertical velocity was 0 meters per second. I then knew that I was able to use the equation VV2 squared equals VV1 squared plus 2a delta displacement. I then began to isolate for the displacement and place my values into the equation. Finally, I was able to figure out that the distance between me throwing the beanbag to the maximum height was 7.97 meters, and since I threw the beanbag at a height of 1 meter, the maximum height was 8.97 meters. In order to visualize how Make the Stick Jump could be played on different planets, kinematic concepts are needed. Firstly, it is important to remember that the horizontal velocity that the beanbag has does not impact the vertical velocity, as they are components. On Earth, if a beanbag is launched with a vertical velocity of 12.5 meters per second, I could find the time it takes to reach the ground by using the following equation. VV2 equals VV1 plus AG delta t. This gave me the time it takes for the projectile to get to maximum height. To get the total time, I would multiply it by 2. so the answer would be 2.6 seconds. Furthermore, when using the same equation but using different acceleration due to gravity values, I figured out that on Mars it takes 7.6 seconds for the beanbag to hit the ground, and on Neptune the beanbag takes 2.2 seconds to hit the ground. This proves that the more acceleration due to gravity a planet has, the faster the beanbag will come into contact with the ground, thus meaning that the less acceleration due to gravity a planet has, the further and higher the projectile will reach. When on Mars, less velocity is needed for the beanbag to reach the same spot as on Earth, and on Neptune, more velocity is needed. Therefore, people would have to alter how they play on different planets. In physics, a frame of reference is used to determine if an object is moving. It usually involves one object in motion and one object stationary. In Make the Stick Jump, there are two frames of reference. A frame of reference relative to the beanbag and a frame of reference relative to the stick. This concept can help to find out what is moving and at which velocity. Now I'm going to talk about where kinetics is seen throughout the game of Make the Stick Jump. Here are three different free body diagrams of different phases of the beanbag throw. Before any movement, when the beanbag is in one's hand, the only forces acting on it is the force of gravity and the normal force. The forces acting on the beanbag when it's being thrown is the force of gravity, the normal force, and the force applied, which could be split into two components, vertical and horizontal. Finally, if air resistance is neglected, then in the air the beanbag only has the force of gravity acting on it. This is until it hits the stick. Now I will describe how kinetics is used to solve equations. To begin, let's review Newton's laws. His first law states that objects at rest remain at rest and objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. His second law states that force equals mass times acceleration. His third law states that for every action there is an equal and opposite reaction. All of kinetics builds off these laws. This question asks to find the force of the beanbag onto the stick. I am given the velocity, time, and mass of the beanbag. I know that F net equals ma, but I only have one of the three variables in mass. Because of this, I know that I have to find the acceleration of the beanbag. I do this by using the equation A equals v over t. I then inserted the values and found out that it has an acceleration of 16.7 meters per second squared. At this point, all I had to do was calculate the force. I multiplied the mass and the acceleration to find out that the force is 3.34 newtons. Moreover, the force of the beanbag on Neptune would be much greater than the force of the beanbag on Earth. This is because the value of gravity on Neptune is higher. The force of the beanbag on Mars would be smaller because of its smaller value of gravity. Now, I will be explaining how momentum and energy is seen in Make the Stick Jump. First of all, it is important to note that energy is never lost. It is always conserved and redirected. That could be seen in this Newton's cradle example. Energy from one ball is passed on to the next, and then the next, and so on. This cycle repeats until the energy is sent to sound or heat. When there is no energy left in the balls, they will stop moving. Another example on how energy is never lost could be seen in Make the Stick Jump. The beanbag starts with gravitational potential energy. When it is released, it then has kinetic energy. It remains as kinetic energy until it comes in contact with the stick. At this point, the kinetic energy turns into sound and heat energy. This is why the beanbag stops moving. The amount of energy in the beanbag determines what happens to the stick, if it will jump or not move. Nevertheless, it is guaranteed that the energy that the beanbag started with will transfer into something else. Now I will relate some momentum and energy ideas to make the stick jump. To begin, there are three types of collisions: elastic, inelastic, and completely inelastic. Elastic is when there is no loss in kinetic energy. Inelastic is when there is loss in kinetic energy, and completely inelastic is when most kinetic energy is lost. In all of these collisions, energy is conserved. In Make the Stick Jump, when the beanbag hits the stick, it is an inelastic or completely inelastic collision. This is because most, if not all, of the energy is transferred from the beanbag to the stick and the ground. The beanbag would keep its energy for a bit, but will lose it after it rolls on the ground. Now I will relate the ideas and concepts from fields to make the stick jump. I will be going over two types of fields: magnetic fields and gravitational fields. Magnetic fields are fields that describe the magnetic influence on moving electric charges, electric currents, and magnetic materials. Magnetic fields could be seen in small things such as fridge magnets or large things like the Earth. The right-hand rule and left-hand rule could help you to determine different things about the magnetic field. This image describes how to use the two rules. The Earth also has a gravitational field. Gravity is a force of 9.8 meters per second squared on Earth. This force attracts stuff to the center of the Earth. The gravitational force of Earth plays a great part in Make the Stick Jump. From the moment the beanbag leaves a player's hand, 9.8 meters per second squared is acting on the beanbag. What the gravitational field does is bring the beanbag towards the ground. Without it, the game would not be possible, as the beanbag needs to fall towards the ground in order to hit the stick. Since Mars has a gravitational field strength of 3.7 meters per second squared, the beanbag would take longer to hit the ground. Whereas on Neptune, the gravitational field strength is 11.2 meters per second squared. This means that the beanbag would hit the ground faster. Although some more than others, it is evident that every unit has something to do with Make the Stick Jump, and without each of them, the game would not be possible. Finally, after immense research, it is clear to me that Make the Stick Jump has to be played differently on each planet. Many factors of the game would need to be altered due to the change in gravitational field strength. Make the Stick Jump is a historic Aboriginal sport that brings families together, but it would not be possible without the help of physics.